Okay, this is lecture 22 for the transient simulation of semiconductor devices. So this is the section for transient simulation, and in this lecture, today's lecture, we will consider an RC circuit as an example. So this slide is copied from our previous lecture 4. So do you remember lecture 4? So lecture 4 was devoted to the diffusion simulation. So at that time, although the problem was not the semiconductor device simulation, but it was process simulation, but anyhow we did certain transient simulation. At the time, I introduced two different Euler schemes like forward Euler scheme and backward Euler scheme. So in the case of forward Euler scheme, we calculate the time derivative using the future value and present value. And in the case of a backward Euler scheme, we use present value and past value to evaluate the time derivative. So I will just consider. So previously we considered this backward Euler scheme, and today we will also use this backward Euler scheme. So forward Euler scheme is not used in the device simulation because it becomes unstable without having quite a short time distance between two neighboring time instances. So this scheme becomes very unstable. And actually there is one subcategory of device simulation where the forward Euler scheme is actually used. So that is stochastic Monte Carlo simulation. In this simulation case, we use the forward Euler scheme to make time integration, but this is not directly related with our conventional device simulation using the drift diffusion model. So this is completely different from that one. So in that case, we use forward Euler scheme, but this is quite special. And today we will talk about the backward Euler scheme. So now think about an RC circuit. Here we consider a series RC circuit, and it is driven by this input voltage source V sub in. Of course, this is a time dependent voltage source, and before the zero time instance it was 0. So since this is 0 volt, everything is just 0. Here we have 0 volt. And typical case we consider is, for example, we just lamp up rapidly, almost immediately, and see what happens to this Vx value. So VDD. What you can expect is eventually this is VDD, so this becomes VDD, and if we go to the another steady state, then actually this one does not play any role, just considered as a disconnected line. So eventually this V sub x will approach to VDD. However, we have some transient behavior before eventually reaching to, so starting from 0, and eventually it will become this VDD value. And how about the intermediate behavior of our V sub x? That is just a matter of concern in our problem. So let's go to this equation. So this equation is nothing but just applied Kirchhoff current law for this V sub x node. So this one is corresponding to the capacitor current, so heading in this direction. And also we have another resistor current. However, since this is positive and this is negative, its direction is also heading in this way. So you know that in this case here, my branch currents are outgoing, so escaping from this X node, and we just keep the sum of these two outgoing currents and it should vanish. So that is quite easy to understand. Then let's go to the analytic solution. So since this is the first order differential equation, its solution is not that difficult, especially when we have just a sudden switch to VDD from 0 to VDD immediately, then our solution will become in this form. So as you know, as you might expect, so this is a time variable, and although our input voltage suddenly ramps up to VDD, our solution V sub x takes some time to reach this VDD level. So there is the relaxation time of RC, so there will be certain time RC, and within a few of RC time constant, then this transient effect will be diminished and we are quite close to the VDD. So are you with me? Now I assume that everybody can understand this one quite easily. Then now let's go to the case where we apply the backward Euler scheme to this simple, really simple problem. So first of all, we assume a constant time step delta t. Is it mandatory or not? Actually, it is not. So sometimes we can control the time difference between different time instances, for example. So if this is, for example, 1 second, there is no restriction like this. Another time spacing should be also 1 second, for example. If this is 1 second, but we have freedom to choose this one 2 second or just a half second, so it is up to us. However, in this simple discussion on the transient effect, we will just consider a constant time step. So please understand this restriction. And then now we can say every time instance can be represented by an integer multiple of delta t. Okay, so for example, what is t10? So this is 10 times of delta t. What is 20t? Then this is 20 times delta t. So I think that this is not that difficult. Of course, I should be a positive integer because I equal to 0 is reserved for our time instance 0, and in this case we just say v sub x at t sub 0 equal to identically 0. So this is the initial condition, and let me just apply or discretize the KCL. In this case, yes, this branch current, resistor current does not change at all because there is no time derivative. The only part affected by this time discretization is this one. Here we have applied once again backward Euler scheme. So now we take the difference between the present value of our voltage and previous value of our voltage and takes the difference. Yes, I think that we have already done it with diffusion simulation, so most of you are quite much familiar with this procedure. So after that, it is recognized that yes, this is unknown variable and this is unknown variable, and there are some known variables like this one. This is known because we have already considered this t sub I minus 1, so this is known and memorized in our computer storage. And here we have input voltages, and this value is given from the functional form of our input voltage. So these green ones, green boxes, just shows unknown quantity, and this purple one shows known quantities. So simply considering only this unknown quantities in the left hand side, and all of known quantities are moved to the right hand side, then we can find this kind of expression. So are you with me? So if you have any question, then please interrupt me.
약간 바이오스 램핑하고 비슷한 경우도 할 수 있을까요?
Yes, of course, but that is really good question. So let me repeat his question once again. His question was, previously we have studied something like bias lamping. So think about a PN junction we have considered up to now. Then if our goal is to achieve 1 volt, then we start from 0 volt and move to 1 volt, and it is, for example, changed from 0.0, 0.05 volt and 0.1.0 volt. So eventually we end up with this 1 volt. That was done in our bias lamping. However, I wanted to stress that the difference between today's transient simulation and previous bias lamping is really significant. For example, in this, let's assume that once again we wanted to increase our anode voltage from 0 to 1 volt. Then we can start from 0.0 volt and increase it to 0.5 volt. Yes, and eventually we will end at 1.0 volt, seemingly quite similar. However, what is the difference? In this case, there is no consideration about the time difference between this and that bias condition. Actually, we assume that infinitely long time has passed once we place once we set our bias voltage, anode bias voltage to 0.05. We just infinitely long wait for the response, steady state response. Only after taking the steady state response, then we lamp up. Then wait for long time. That is the situation. However, in this case, although we follow the same voltage steps, but there is always a certain time difference between 0 and 0.05 volt. So if this time difference is short, then there will be certain contribution from time difference form. Of course, let's say that if this time difference is quite long, if delta t goes to infinity, then our transient simulation result will follow that of just conventional DC bias condition, bias lamping simulation. However, if we have quite short, reasonably short time differences, then that will make a huge difference in your calculation result. That was a really good question. So I never thought about that question because to me it is too natural, but as a newcomer, that is quite a reasonable question. So compared with just DC simulation, DC bias lamping, although bias is uh, incrementally changed, but they are quite much different. Simply speaking, in this bias lamping, all of time derivative terms go to zero. We intentionally neglect this one. However, in the case of transient behavior, transient simulation, actually this treatment of time derivative term is the most important one. So yes, that was a really good question. Okay, do you have any other question? So please feel free give me a question, because as we have seen just before, sometimes I just skip something because I think that that is too obvious to everybody, but sometimes that is not that case. So please let me know if you have any unclear one. So okay, then let's continue our discussion. So our present example means that just sudden switch at the time equal to 0. In this case, for our positive I values, I equal to or larger than 1, it is always, the voltage source is always a constant VDD. Okay, so here we have constant value. So now in this section, I wanted to consider the impact of a time step, so delta t. Since there are many different parameters, so I wanted to make a normalized expression. So here R, C, VDD, all of them are set to be 1 with their own dimensions. So it means that R is 1 ohm, C is 1 farad, and VDD is 1 volt. Maybe you say that, okay, this is too large. Yes, I know. Actually, the farad capacitors of our transistors can be much smaller, nanofarad or picofarad or sometimes femtofarad. So this is extremely small quantity, but you know that I just wanted to relative importance of delta t. So all of these quantities are just set to be 1. In this case, the equation is simply can be written as this form. Why? So please come back to this one. I just to say that R is 1, C is 1. So here we have RC equal to 1 plus delta T. And here we have also 1. And this one also becomes VDD, but in this case we have 1 volt. So that's the reason why we have an extremely simple form of 1 plus delta T times our Vx equal to our previous value of V sub x plus delta t. Yes. Also, since we have VDD equal to 1 volt and RC time constant is 1 second, so we have also quite a simple expression. So now with this all of these normalized quantities, then only difference or only quantity we can control is delta t. So I wanted to try different delta t. Of course, if delta t is too large, like for example 100 or 10, that doesn't make any sense, because this system behave like a certain relaxing system, and its relaxation time is just set to be 1 second. So if we say delta t equal to 100, then every relaxation will be inside one step. So if you take this kind of thing, you never observe any kind of transient behavior. Also, this is obvious. So please do not consider this extremely large value, unphysically large value for your delta t. If you wanted to trace the change of your node voltage V sub x, then you have to have reasonably small delta t compared with the relaxation time 1 second. So now let's go to the case study. Delta t equal to 1 second. So you feel that this is too crude. Yes, that is too crude. So because it's the system, in every 1 second, your uh, your node voltage, so measured from this VDD, previously it was 1. However, after 1 second, it will be just e to the minus 1. So there will be significant change within this 1 second. But if you use this quite large value, large time step for your simulation, what you can expect is, of course, your simulation will be done quite a short time because you have only, for example, 10 points from 0 second to 10 second because you have just delta t equal to 1 second. But its property or its quality, the solution quality will be quite bad. So please have a look at this one. Exact analytic solution is drawn as blue curve. Why do we have this piecewise linear behavior? Because I just drawn at a given time instances. So this is actually analytic solution, so smooth curve. And this red one, this one is the numerical solution obtained with delta t equal to 1 second. So are you happy with this red curve? So certainly not. It contains a lot of error, and error means that compared with this exact analytic solution, the difference from that solution is measured, and as you can see here, this is the error level. The maximum error in its absolute value is more than 0.1 volt. Significant error is observed. But you all understand this situation because we have used two large steps for transient simulation. Then how about going to a little bit more refined system or refined time step? In this case, we have already made 10 times shorter time spacing, and it is the result. So now your blue curve analytic solution and red curve numerical solution seems to be agree much better. So maybe you agree with me, and this is the error, and you can see that the error occurs, the maximum error in its absolute value is about just 0.02 volt. Okay, so compared with our previous value, it is much improved. But although it is more or less reasonable, but still we have some certain differences, and it is larger than 0.01 volt. Then how about decrease our time spacing even further? For example, let's go to the 0.0 1 second. Then can you see the difference between blue and red? Yes, if you have a quite good vision, then maybe you feel blue dots and red dots, blue pixels and red pixels in this one. Maybe there is a mixture of blue and red, but anyway, it is almost invisible in this metric graph. And sorry about that. So I made mistakes. We have to say this maximum absolute difference now becomes about 1.8 times 10 to the minus 3 volt. So can you write down the difference? In this case, its value was 18 times 10 to the minus 3 value, 18 millivolt. And you can see that here we have 1.8 times 10 to the minus 3 volt. What is the difference between this and that? You can understand there is a 10 times reduction of what? Reduction of your error. I mean that, simply speaking, your error is proportional to delta t. If you shorten your time difference 10 times, then you expect that error is reduced linearly by this uh, discretization scheme for time difference, because we are assuming the piecewise linear behavior of our curves. Okay, so now you can, for example, you can try once again. It is your own exercise. Please try to simulate the same system with 10 times shorter time difference. Then what is your expectation about the error value? Maybe you will get another 10 times smaller values, 10 to the minus 4 volt. Okay, so this was the backward Euler. So then let me just tell you the reality, the practice. How about the use of backward Euler? Even when you use the commercial ticket simulator, there is an option for using backward Euler model. So this is really being used in reality. So this is one, but sometimes if you need better accuracy, higher accuracy, then you want to avoid the use of backward Euler. So sometimes in this case, if you are in hurry, oh, I have to find the result, and your accuracy is not that much big concern, then you select backward Euler. However, sometimes you wanted to really accurate result, then although spending more time, then you want to have a better result. Okay, so now we'll talk about another method, another representative method for this time derivative. Of course, I wanted to stress that this is not the only way we can have the transient simulation. There are many other different methods, and especially for this device simulation, drift diffusion model, actually this model is not used because we have even better model for time derivative. So I wanted to say I don't want to go too deep into this topic, but so what they do in reality is starting from this previous past time value to this new time value. So in practice, they introduce a certain intermediate step. So, and for this intermediate step, they apply a certain time derivative behavior, and another second internal step, they introduce another uh, time derivative step. Why they do so? It is because uh, backward wheel scheme. How many memories are required for your implementation? In order to calculate this backward wheel scheme, then you have to know the value at your present value and your previous value. Only two quantities were required. However, from now on, we wanted to consider even better model. Uh, then how can you make an even better model for time derivative? The best way is not only considering this present value and previous value, taking only two and having the linear dependence on the error, dependence of error on the time spacing. But if we expand the dependence to the second past time instances or third past time instances, if we consider the history of our trajectory, then we can find better accuracy for our time derivative term. This is general consideration. So the limitation of backward Euler is it is simple because we consider the first the closest past time instances. However, if we consider more and more time instances, then our schemes get more complicated and gets more accurate. So are you with me? So that is the scheme we have. So now think about this one. Here we have only two time instances, but we wanted to get, for example, three time instances. Then how can we generate one more time instances in this scheme? What they do is first go to this intermediate internal steps using this linear scheme. Then now you have uh, t sub I plus 1 and t sub I minus something. So this is not exactly half, but anyway you have something. This question mark is smaller than 1, and after that when you really calculate this time derivative at this point, fortunately you have two past time constant time values. For example, you have the solution at this time constant time instance, and also you have another one. So you take both of them as a past value, first past value, and second past value. So you apply second order method for your t sub I. So at the first glance, it sounds really strange and crazy. Why we have to introduce intermediate steps and makes the integration twice, something like that. But please note that sometimes accuracy of a transient simulation is so important. For example, if you are considering the simulation of your NAND flash, then in this case, the accuracy of your time integration really determines whether your charge stored in certain memory unit is kept or just lost. Also, another memory device, DRAM, has the similar problem. So, accuracy of time transient simulation is sometimes quite critical. So that's the reason why, although this kind of implementation requires a lot of additional burden for developers, but they are willing to spend more effort to have this kind of implementation. So within a single time time interval, they intentionally introduce intermediate step and apply two different one. So simply speaking, for this first step, they just apply the trapezoidal rule to the first step, and second step they apply Gear's second order method. Then I will talk about Gear's second order method. I will not talk about this entire scheme, but I will just consider Gear's second order method. The main message I wanted to deliver to you is, okay, if you adopt this second order method, the accuracy of your calculation can be improved greatly with shorter delta t. Okay, then following the same argument, let's assume a constant time spacing delta t once again. Then for time instance where I is larger than or equal to number 2, then we can express our time derivative in this way. So can you understand the difference between this one? So this is Gear's second order method and backward Euler. When you consider backward Euler, it was FTI minus FTI minus 1. So what is the difference? The difference can be like this. Here we have minus 2 and this is minus 1, and here we have 1.5 and here we have positive 1, and instead of that here we have additional factor like additional dependence on second past time instance. So that is the difference for our Gear's second order method. Then of course let's assume that all of these kind of schemes should vanish when f if all of them are the same, then time derivative should vanish. Can you recognize it? Because this is 1.5 minus 2 and positive 0.5, sum of them is just 0, so time derivative vanishes. Okay, then obviously when I equal to 1, that introduce problem. Then it is t1 and t not. Okay, we know it. However, t I minus 1. Sometimes it is difficult to say what is value of our previous second previous value at the initial point of our calculation. So for this very initial point, the trick is just to use the backward Euler scheme in order to initiate the initial problem. Once you prepare the t0 and t1 values, after that from t2 you can consider t2, t1, t0 to calculate the Gear's second order calculation. So now your KCL now looks like this. This one is never changed, and here you can see that dvx over dt is now written as this form. Seemingly a little bit more complicated, but don't be afraid, because once again only unknown variable is shown here. These are unknown variables and they are past values, and this is a given function of time. So after rearranging terms, then we can easily understand this is the form for our v sub x when everything is normalized. R equal to c equal to v dd equal to 1 with their own unit values. So please make a comparison between your new expression with Gear's second order method, and this is your backward Euler. So difference is highlighted here as a red color. Here 1.5, 2 and minus 0.5 is shown here, and previously we had no dependencies on this t sub I minus 2 quantities, and now we have introduced this one, and also coefficients are slightly different. Well, anyway, seemingly it is quite easy to implement. So then let's go to t delta t equal to 1 case. Once again, this blue one is analytic solution, and this red one is the numerical solution with Gear's second order method. So in this case, actually the maximum error occurs at 1 second, and this is obtained from what? Obtained from just backward Euler scheme. So backward Euler scheme determines this the very first time step, so it's not related with our Gear's second order method. And anyway, we have similar level of error. And now we wanted to reduce this delta t to 0.1 or 0.01. What will happen to our error level? So now let's go to 0.1. So now this is the result. Good. And you think that maybe backward Euler scheme already gave you quite good agreement, good reasonable result for this 0.1 volt. But please make a comparison. So this is the one for Gear's second model, second order method, and when you come back to this one, yes, it was that of backward Euler. So although small, you can clearly observe a small difference, and its value was, the maximum error was about 18 millivolt. And when you go to this case, then can you see the difference? Actually not, and the difference is about 5 millivolt. More than 3 times smaller error is obtained with the same delta t. But the real strengths or real advantages of this Gear's method comes to the small, even smaller. So sorry about that. Here I have to say that this is with Gear's method once again, and this is the result of delta t equal to 0.01 second. So once again we have quite good agreement. Actually, even to me, I cannot make any distinction between these graphs, the left graph and this graph. They are all good, but point is, when we numerically calculate the difference, the error, Now its value, absolute value is just given by 10 to the minus 5. And you know why do we have this value? Yes, so it is originated from our backward boiler, and error is rapidly decreasing. Okay, so the main message is previously when delta t equal to 1, then backward boiler and gear, their error value was quite similar, and delta t equal to 0.1. Now we have 18 millivolt and 5 millivolt. Okay, then when it go to 0.01, and it is linearly decreasing like 1.8 millivolt, but now this one becomes just 70 microvolt. So are you with me? Simply speaking, when you go to even shorter time distance, then it will be just 0.18 millivolt, but you can expect that you will get even smaller values for your error for this transient behavior. So in summary, the error is rapidly decreasing with a smaller delta t. This one is linear scheme, so error is more or less linearly dependent on your delta t. Gear's second order method is a second order method, so the error is more or less proportional to the square of delta t. So even though for larger value they show comparable behavior, but if we go to refined simulation with delta t is small, then we can approach to much better result more quickly with small delta t at a given delta t value for gears second order method. Okay, so therefore selecting better method is quite beneficial for your accuracy. Then my question is, wow, then everybody just takes a gears second order method? Uh, Unfortunately, sometimes it is not, because in practice there is some consideration. So we now all know that this is much better in terms of accuracy. However, in its implementation, what is the disadvantage of this gears second order method? So, for example, we must introduce this past value. Simply speaking, your previous solution should be in your computer memory. So it requires additional memory requirement for your simulator. So in this simple problem, this is just one single double precision number, so it's not that much. However, if you are considering the 3D simulation, wow, what will happen? This is a huge vector you have to memorize. Okay. However, nowadays, nowadays memories are quite cheap, so this one can be easily done. So in many cases, so it is not that much difficult to implement Gear's second order method. Okay. So simply speaking, backward Euler is the simplest one in its implementation and the cheapest one in its actual use. However, in terms of accuracy, it is not the best one. So with more computational effort, we can improve the situation. Okay. Then I have prepared our last example. Hmm, we have the same RC circuit, but now instead of just a sudden switching, now let's apply a sine wave and its amplitude is 1 volt. Okay, so what will happen to this system? So now we have R and C and apply sinusoidal wave. Um, the behavior of this system is quite easy. If we apply quite slow signal which has very low frequency, then in this low frequency case, actually our capacitor still working as a disconnected line, so high impedance. So our applied voltage will be just copied into this Vx node, so we will get the same behavior. However, if we go to sufficiently high frequency, then what will happen? In this case, the impedance of this capacitor is significantly reduced. So now the output voltage, so V sub x, will be diminished significantly. So simply speaking, the impedance of this R is always R. However, impedance from this C is given by just 1 over j omega c. So you know this j is imaginary unit. So in physics department they use it as I, but in engineering part we prefer to use j instead of I, and omega is just 2 pi times frequency f. So the steady state form of our V sub x is simply given by 1 volt, the amplitude of our input voltage, and given by 1 over j omega c and series impedance of 1 over j omega c and r. And eventually, when you take the amplitude of this V sub x, then it becomes like this.
Yeah.
1 plus omega rc square. That is the expected behavior of our V sub x, its amplitude. So in this specific case, what we have assumed is, okay, r equal to 1, c equal to 1, then the remaining question is, what is the frequency? In this specific example, I just said the frequency is 1 Hz. So omega becomes just 2 pi and its value is now 1 plus 2 pi square. So this will be the amplitude of um, our V sub x when the transient effect is all gone and when it becomes stabilized. So its value is about 0.15 around something. So now let's try to simulate with this case. So now the only difference is previously we said V in equal to VDD for every case, but now it is no longer the case. We have to keep the value of V in. So can you see it here? So it is shown here. Now instead of just number 1, I just introduce sine 2 pi t because f frequency is still 1 Hz, So that will be the value of input voltage. So with this change, we can just reuse our previously implemented code. Then you can easily understand what is the difference between your backward Euler and Gear's second order method. Then let's go to the case. So I have just to show you one specific case, delta t equal to 0.01. So why don't we just try 1 second or even different values, but this is not that good for our comparison, because if this is too large, then actually the simulation results are not that good. So now we have all, sorry about that. Sorry about that. I'm not quite sure about that. So I think that this is correct and only 10 points. No, so I will figure out what is the actual value I have used in this slide. But anyway, we have used a given delta t value, and I just ran 20 cycles. Since the period is just 1 second, so I run the simulation up to 20 seconds, and this is the behavior. Once again, blue is our, oh sorry about that, backward Euler, and red is our Gear's method. So for this value, it looks already good to have it. So initially we have a certain transient behavior. After that, this is gone, and now we have a well stabilized response of our input signal. Since we have applied sine signal, also we can expect there will be certain sine signal or cosine signal with the same frequency. That is the situation shown here. And you know that if everything is perfect, then our solution should have this value as its amplitude, 0.157. And here you can see that we have this level as a perfectness of our numerical solution. And how about the result from backward Euler? Okay, backward Euler shows the peak value quite close to the ideal value, but still it has difference. Also, in the case of Gear's method, the solution is not perfect. Still, we have difference. But you know that the difference between the analytic solution and the obtained numerical solution is much smaller than that of backward Euler. So what we can observe from this sinusoidal one, and also another one for our stepwise excitation, is if you take this Gear's second order method for your calculation, then you can improve the accuracy of your calculation. That is the main message I wanted to deliver to you in today's lecture. Then today's lecture was devoted to what? Devoted to a simple RC circuit. Why did we spend one whole lecture hour to this one? So now you are much prepared to apply this technique to what? To the simulation of your semiconductor devices. So in your semiconductor devices, you can find some time derivative quantities. Up to now, you have neglected them. For example, you neglected round n over round t originated from electron continuity equation. Also, you neglected terms like this round P over round T originated from the whole continuity equation. So now, with this technique, we can add those components into our simulation. Then we will see what happens in this device simulation. That is my plan for next lecture. So are you with me? And do you have any question? If you have any question, then please let me know.
그 계열주 메소드에서
Yes.
네, 그 ti와 ti-1와 그리고 ti-1, ti-2 그 미분을 디스크리타이제이션 하는 쪽에서 개수가 다른 게
Yes.
앞에 그 바로 전 타임에 대한 어떤 디펜던시를 높이기 위한 건가요?
Yes, sure. So, let me just repeat his question. So he told me that here we have a quite seemingly quite a strange coefficient, and he observed that this is a present value, and here we have two different past values, and they have number 2 and number 0.5. Is it related with the relative importance of the very first past value compared with the second past value? My answer is yes. Obviously, this is a directly past value, and this is a second past value. Obviously, this one is more important than that one. And another one I wanted to stress is here you can not only just the magnitude difference, but also here you can see that this one has negative sign, but it has not negative sign. It has a positive sign, and its positive sign is a coincidence with that of present value. So yes, simply speaking, although both of them are originated from previous time instances, but this is really corresponding to the direct past value, and actually this one is used to correction according to the second order expression. So if we have, for example, let's consider a parabola. If we have such kind of a parabolic waveform, then if we wanted to calculate the derivative in this case, then usually what we can do is just to consider difference and assign it into here. Then this is the first order method. However, if we have the second previous time, then we just consider a parabolic curve matched to these three time points. So we make a certain estimation about function itself using these three time instance values, t1, t sub I, ti minus 1, and ti minus 2. So are you with me? So since we have three different values at three different time instances, then actually these curves can be matched a parabola, because a parabola need ax equal square bx plus c. It has three different unknown variables, and with three different time instances and function values, we can find a certain form. From this one, this time difference was obtained. So simply speaking, the better approximation or better result obtained from here's second order method is basically the assumed waveform is higher order than the backward Euler. So in this case, we can expect better expectation. And also, if you have this quantity, if you know this and that, so if we go to this way, then maybe this is like this. And if we go to even lower values, then we can control it more steeper way. Okay, so yes, so it has quite much different behavior than the change of this direct past value. Okay, so that was a really good question. And simply speaking, although the derivation is not shown here, so from the viewpoint of Gear's second order method, they means that this first one and second one play a completely different behavior, so they have a different role, so that's the reason why we have a different coefficient for them. Okay, good question. And any other question for okay, before wrapping up today's lecture, I wanted to stress that we have although we have considered this time transient method, and eventually will apply this method to the device simulation, but I wanted to stress that this technique is equally important to a neighboring research field called as circuit simulation. I mean that eventually we will use this kind of discretization to solve drift diffusion model. However, the current problem is not the device problem, but it was KCL. And KCL is the very governing equation of all of circuit simulation, so SPICE simulation. So simply speaking, circuit simulator developers are even more interested with this technique because to them, although the system itself is quite simple, but they are really critical to find out the waveform, time-dependent waveform of their voltages and current. So they have tons of different methods to control the accuracy. Especially the main trick is controlling the time instances. Up to now, I just considered a constant time differences, but in the case of circuit simulation, the controlling delta t to minimize the error and at the same time not increasing the computational burden significantly. That is the real trick, and that is an art, and there has been tons of efforts to achieve that goal. So I wanted to stress this one because some of you are interested with circuit simulation. Okay, so do you have any question on today's lecture? No? Then, although we have 5 more minutes, I want to wrap up today's lecture. Thank you for your attention.